Dear students, I am Mayuri Gatme, lecturer, Computer Engineering Department, NIT Polytechnic, Nagpur. So today we are going to see unit number 5 and topic 5.2, which is interpolation and types of curves. So what is the prerequisite knowledge? We have to know the basic knowledge of coordinate system and DDA arc generation algorithm, which we have seen in previous lecture. Course outcome and program outcome. CO5 develop program to create curve using algorithm. Program outcome: basic knowledge, discipline knowledge, ethics, individual and teamwork, communication and lifelong learning. So, interpolation. Before starting interpolation, what we have discussed in previous lecture, we have seen limitation of true curve generation approach. Furthermore, in practice, we have to deal with some complex curves for which no direct mathematical function is available. Such curves can be drawn using approximation techniques or approximation methods. So, if we have set of sample points which lie on required curve, then we can draw the required curve by filling the portion of the curve with the piece of known curve which pass through nearby sample point. The gap between the sample point can be filled by finding the coordinates of point along the known approximating curve and connecting through point with a line segment. Okay, so this definition is known for unknown curve. See the first diagram, which is unknown curve. So the main task in this process is to find a suitable mathematical expression for the known curve. If we have the mathematical expression for the curve, then how to represent it? So the polynomials, trigonometric, exponential and other classes of function that can be used to approximate the curve. Usually the polynomial functions in parametric form are preferred. The polynomial function in the parametric form can be given by x equals to f, which is known as function of u, y equals to fy of u and z equals to fz of u. So we can realize from the above equation that the difference between 2 and 3 dimension is just the addition of the third equation for z. Furthermore, the parametric form treat all the 3-dimensional equally and allows the multiple values, that is several values of y or z for a given x value. Due to this, multiple value curve can double back or even cross themselves as shown in the figures. So the very first diagram we see is unknown curve. Second is known sample point. Third is filter region with known curve. Then we have to calculate more point from the known curve and actually draw the straight line segment connecting the point. So we have seen that we have to draw the curve by determining the intermediate point between the known sample point. This can be achieved using interpolation technique. So now let us see the interpolation process. So suppose we want a polynomial curve that will pass through n sample points. So x1, y1, z1, similarly x2, y2, z2 up to xn, yn, zn. We will construct the function as the sum of the term, one term for each sample point. So if we are talking about each sample point, then how can it represent in the function form? Fx of u equals to limit I equals to 1 to n xi bi of u Similarly for f, y, u and similarly f, z, u. So these were the three functions. We will construct the function as the sum of the terms. So what is BIU stand for? So this is the blending function. For each value of the parameter u, the blending function determines how much the ith sample point affect the position of curve. In other words, we can say that each sample point tries to pull the curve in its direction and the function bi of u for other values of I. Then ith sample point has control of the curve and curve will pass through ith sample point. So by applying this, we will able to draw the known curve. For different values of u, some other sample point may have complete control of the curve. In such cases, the curve will pass through that as well. So what we see the blending function and how we are able to write in the form of the functions. So assume that the first sample point is x1, y1, z1 has a complete control. Similarly, you have to see the diagram. See, here diagram is given one simple curve and u value varies from -1, 0, 1 by 3, 2 by 3, u equals to 1, u equals to 2. So, how many values we are getting? For u equals to n minus 2. Till the limit we have to subtract 2 from it. So, assume that the first sample point x1, y1, z1 has a complete control when u equals to -1. The second, when u equals to 0, if we are incrementing the value of u by 1, then obvious -1 is incremented to 0, then 1 and so on. So on till n minus 2. When u equals to -1, so simply put the values in the formula of b of I. So b I of u, that is b1 of u equals to 1 and 0 for u equals to 0, 1, 2 till n minus 2. What they are saying, if you are putting the value of u equals to -1, then you will get the value of b of u equals to 1 and you will get the value of b1 of u equals to 0 if you are putting the value of u equals to 0 to n minus 2. See, similarly, when u equals to n minus 2, what value you get? For b, n of u equals to 1 and for 0 of u equals to -1 to 0 till n minus 1. So, similarly, we will able to find out the value of b1 of u. To get the value of b1 of u equals to 1 at u equals to -1 and 0 for u equals to 0, 1, 2 and minus 2. The expression for b1 of u. Then how we will able to calculate the expression for b1 of u, which is given by the formula u into u minus 1, u minus 2 till u minus n minus 2, because the limit for u is from -1 to n minus 2, divided by -1 into -2 till 1 minus n. So where denominator term is a constant use. In general, for ith blending function which is 1 at u equals to minus I minus 2 and 0 for other integer can be given as. If you are able to calculate the value of b1 of u, then definitely you will able to find the ith blending function. So bi of u equals to, the given formula is u plus 1, u minus 1 till u minus I minus 3, u minus I minus 1 till u minus I minus 2, divided by I minus 1, I minus 2, I minus 3, 1 minus 1 till I minus n. So what is this formula? Which is nothing but we call it as an whenever we get this expression, see, and the approximation of the curve using the above expression is called as Lagrange interpolation. See, whenever you are getting the approximation of the curve using the above expression, we called it as Lagrange interpolation. Then, from the above expression of blending function, in previous slide, we will see the blending function. So, now how to calculate the expression for blending function for 4 sample point. Assume that we have the 4 point on the curve. Then how we are able to calculate the blending function? Then B1 of u, B2 of u, B3 of u and B4 of u. So simply you have to place, instead of I equals to 1, then I equals to 2, I equals to 3 and I equals to 4 in the blending function expression. Then using the above blending function, the expression for curve passing through sampling point can be realized as follows. So x equals to x1 b1 of u plus x2 b2 of u plus x3 b3 of u plus x4 b4 of u. So what is the reason we are getting here 4 values? We are adding only 4 values because we are working for 4 sample points. That's why for x, y, z we will get the b1 of u, b2 of u, b3 of u and b4 of u. So this is the interpolation. In interpolation we are seeing the blending function, and whenever the approximation of the curve is done using expression, we called it as Lagrange's interpolation. Then conclusion is, we have covered the interpolation topic from unit number 5. Topic is 5.2. Then assignment number 5.2, the very first question is, define interpolation for 2 marks and what is blending function also for 2 marks. So these were the important MSBT questions. So in next lecture we are seeing the types of curves. So in under types of curve we will see Hilbert curve. After that Bezier curve, Hilbert curve, Bezier curve, midpoint approaches. So this type of curve we are going to cover in the next lecture. Thank you dear students. Keep learning, enjoy learning.